Section 6.7 Hyperbolic Functions. This section will be based on a type of figure that is used a lot in applied mathematics. We see this a lot when we think of like the wires and the cables, electricity cables in architecture, and waves, and so on. Here we'll learn how to work with such type of functions. To begin, let's read it from our text. Certain even and odd function combinations of exponential functions e to the x and e to negative x arise so frequently in math that they deserve their own special names. In many ways, they are analogous to the trig functions, and they have the same relationships to the hyperbola and the trig functions have in the circle. For this reason, they are collectively called hyperbolic functions and individually called hyperbolic sine, hyperbolic cosine, and so on. So hyperbolic sine, we'll see that as sine but with an h. Hyperbolic cosine, cosine but with an h. And you can guess tangent. Hyperbolic tangent would be tangent with an h. I've often heard like my professors in the past called it sinh and cosh, but then I don't know what they call the rest. So I'll just refer to them in the future as hyperbolic sine and hyperbolic cosine. All right, so how do these functions come to be? Here we have their graphs. To begin, we have our hyperbolic sine graph, and we see that's made up from this blue line, which is y equals 1/2 e to the x, this green line, negative 1/2 e to the negative x, which produces our y equals sine, our hyperbolic sine graph in red. We see that for cosine as well. Similarly, we have our y equals 1/2 e to the x, just like in the other one. But in this one's reflected over with that negative. So now we have positive 1/2 e to the negative x. And in red, we see our hyperbolic cosine. And here we have our hyperbolic tangent. These functions are in use in applications such as to describe the shape of a hanging wire, like an electricity wire, or describing ocean waves. And here are functions which we just saw the graph of. So we see that hyperbolic sine of x is e to the x minus e to the negative x divided by 2, which were our functions that were graphed. Our hyperbolic cosine of x was e to the x plus e to the negative x divided by 2, and our hyperbolic tangent is made up of hyperbolic sine divided by hyperbolic cosine, and their inverses, not their inverses, their reciprocals are also listed. We will talk about inverses soon. And with hyperbolic identities, we also have a lot of those trigonometric identities that you learned back in pre-calculus. So remember, sine is one of those odd functions, meaning if we have a negative in our output, it translates to the negative being outside of our function. Cosine is an even function, therefore hyperbolic cosine is also an even function. So if our argument is negative, it gets worked out to be positive. We also have our Pythagorean identities, which we see here. Recall them from when we worked with all those proofs back in pre-cal. And we also have our difference in sum for sine and cosine, but now we have them for hyperbolic cosine and sine. All right, so let's take a look at an example. Prove that hyperbolic cosine squared minus hyperbolic sine squared of x equals 1. All right, so to prove that it's equal to 1, why don't we try using their definition? So right above, we have their definition for the function. We're going to use that to replace hyperbolic sine and hyperbolic cosine. I am sure that something will unravel once we do so. So hyperbolic cosine squared is e to the x plus e to the negative x divided by 2 minus hyperbolic sine, we have e to the x minus e to the negative x over 2. And these quantities are being squared. So make sure we write that square. Okay, let's go ahead and expand these squares. So I want to make sure to, in a sense, FOIL your numerator, your denominator. 2 squared is 4. So we have e to the raised to 2x power plus 2 plus e to the negative 2x power. So when I was working these out, I was like, why did that 2 happen, right? Well, we got that 2 because, remember, when we're expanding a binomial, a plus b squared is the same as a squared plus 2ab plus b squared. Remember, it's your e to the x2. Remember your exponent rule, so that's going to multiply the x and the 2 will multiply. And then we have 2 times our a times our b. Well, if we add their exponents, they're 0, right? This gives us e to the 0 power, which is 1. So we're just left with that 2. And for our second term, we have our e to the negative x squared. So just in case you had a little algebra hiccup, I expanded it for one of them. All right, moving forward, we have a 4 in the denominator minus e to the negative 2x minus 2 plus e to the negative 2x over 4. Let's distribute this negative. And we see that our e to the x, our e to the 2x, I didn't write this one right properly. That was e to the negative 2x. So we have our e to the 2x, that was positive, and our e to the 2x add to make 0, our e to the negative 2x and our e to the negative 2x add to make 0, and we're left with 2 minus negative 2, which gives us positive 4. We're left with 4 over 4, which is 1. So it proved that it is equal to 1. Now our hyperbolic trig functions also have derivatives. So derivative of hyperbolic sine is hyperbolic cosine. Our hyperbolic cosine derivative is hyperbolic sine, and so on. Similarly to our trigonometric derivatives. Now, inverses of hyperbolic functions. So similarly to our trig functions, we have inverses. We can go ahead and switch our x and our y arguments to show that our one-to-one domain, our domain and our range change. Here we have our graphs of our hyperbolic inverse functions. We have hyperbolic sine, and notice that our domain and its range is infinite, all real numbers for its domain and its range. We have hyperbolic cosine, and we see that its domain and its range is not all real numbers. Its domain is from 1 to infinity, and its range is from 0 to infinity. And hyperbolic tangent has a domain of -1 to 1 and a range of all real numbers. Since hyperbolic functions are defined in terms of exponential functions, it's not surprising to learn that the inverse hyperbolic functions can be expressed in terms of logarithms. So this is an alternative way to work with inverse hyperbolic trig functions. So let's say in a situation you're left where you have to evaluate. Well, for your original hyperbolic functions, you can rely on these definitions with E. If you're in a situation where you have to evaluate and you have your an inverse, you can work with your newly presented alternative hyperbolic trig functions, which work without n. Moving forward, derivatives of hyperbolic functions. So we have our derivative for sine inverse hyperbolic function is 1 divided by the square root of 1 plus x squared. Our derivative of hyperbolic cosine inverse is 1 over the square root of x squared minus 1. Our derivative of hyperbolic tangent inverse is 1 over 1 minus x squared. And we see that we also have some for hyperbolic cosecant, hyperbolic secant, and hyperbolic cotangent. All right, lastly, let's work with some derivatives. Okay, first one says find the derivative of hyperbolic tangent inverse of sine of x. Okay, so we see that we have a trig function, and trig functions, if we have an argument other than x, we have to follow chain rule. So let's start off by taking the derivative of the outside and then take the derivative of the inside. All right, so just as a reminder, let me write it since we have it so handy. Our derivative of tangent inverse is 1 over 1 minus x squared. But notice, this is because we're working with x, and so that x is being squared. Here, we're working with sine, so be warned. Let's go ahead and apply that derivative. So let's take the derivative of the outside. Let's take the derivative of our tangent. So our tangent would be 1 over 1 minus our argument squared, so that would be sine of x squared. That's our outside. Let's take the derivative of our inside. The derivative of sine is cosine. And we have it. That's our derivative. Now, of course, whenever you're working with our trig functions, we try to simplify as much as we can. So let's go ahead and multiply across. So we have cosine of x over 1 minus sine squared of x. And if you see a 1 and a cosine or a sine squared, or a trig function squared, you should think Pythagorean identities. Remember that cosine squared plus sine squared equal 1. So if we have 1 minus sine squared, that's the same as cosine squared. So let's make that replacement so that we have cosine of x divided by cosine squared of x, which gave us 1 over cosine. And 1 over cosine, we can't just leave it like that. We know that that is secant. So we have secant of x. That is our final answer. Next one. Evaluate our integral from 1 to x. From 1 to 0 of dx divided by the square root of 1 plus x squared. All right, whenever we have our integrals written that way, I always like to rewrite them so that the dx is on the side. Okay. Now, notice on all the previous sections, we have like a whole chart with your derivative rules and then a whole chart with your integral rules. Well, we could do that, but we also can use them interchangeably, right? So we have said in our notes, one of the boxes above says, from our notes, we have that d dx of sine of h inverse of x is the same as 1 over 1 plus x squared, right? So if we're trying to find the integral, you can just go ahead and work backwards. Don't forget that your derivatives and your integrals are like opposites. All right, so let's go ahead and work this out. So we see that the integral of 1 over the square root of 1 plus x squared would be our hyperbolic sine. So our integral is sinh inverse of x from 1 to 0. All right, I'll continue over here. So we're trying to evaluate this hyperbolic inverse function. But do we know how to work and evaluate with hyperbolic trig functions? No, we don't. But again, from our notes, we were told that we can always rewrite them as a logarithm argument. So from our notes, again, this is all from your notes. You have this in the box above. We have that sine inverse of x is the same as the ln of x plus the square root of x squared plus 1. All right, so from our notes, you can go ahead and make that change. So instead of hyperbolic sign, we'll write ln. So we have for 1, we have ln of 1 plus the square root of 1 squared plus 1 minus, and then for our 0, we have ln of 0 plus the square root of 0 squared plus 1. Okie dokie, let's evaluate. So for the first one, we have, let's follow order operations. We have 1 squared plus 1 is square root of 2. So we have the ln of 1 plus square root of 2. And then we're left with minus. Follow order operations. We have 0 squared plus 1, that's 1. So we have the square root of 1, which is 1. 0 plus 1 is 1. And we're left with the ln of 1. When is ln 1? Think of base e. E to what power gives us 1? We have 0. So our final answer is just ln of 1 plus square root of 2. Alrighty, we're all done with this section. This was 6.7 hyperbolic functions. Your homework is numbers 31 through 45 odd and 61 through 67 odd. Thanks.